f of q, let me write. This is the volume integral of now first of all, let us see that suppose I have, remember rho is normalized in this fashion, that is volume integral of rho has to be 1. Alright? Now suppose my charge distribution was point length. Then, of course, you will write rho of x as delta function. Now, those of you who do not know delta function, forget it. But those of you who know, remember that this property will be very much satisfied. The integral of a delta function over a region which includes the point x equal to 0 is indeed 1. That means for a point charge f of q is indeed, so this delta function integration means if you replace this by a delta function, then x is 0 here, and by the property of the delta function f of q will be. Therefore, I am totally justified in saying that this f of q represents the departure from the point-like behavior. Alright, I am fully justified in saying that. Now comes the point that suppose the distribution is not point-like, but suppose that q magnitude is so small that q dot x is negligible over the charge distribution. Suppose for simplicity I am assuming that the charge distribution has a radius r, then the maximum value of this q dot x will be just magnitude of q times r. The angle can at most be 1, so we can forget it. But that q times r is negligible. Alright? Then again f of q will be that is, there will be no departure from point-like behavior. But what does it mean? What is q? Q is the momentum transfer. Now if you look upon this process as the electron goes and some photon interacts with the charge distribution, this momentum transfer q, which is momentum of the incident electron minus then q is basically the momentum carried by the photon, and qualitatively at least, of course it can be justified, q is the de Broglie wavelength of the photon. Inverse of q. The de Broglie wavelength is h cross over p. So h cross over magnitude of q is the wavelength of the photon. Now Q going to 0 means that means that here suppose is the charge distribution. The wavelength is so large, wavelength is inverse of Q. Wavelength is 1 over Q. Q going to 0 means wavelength is very large. That is, the photon is scattered from the entire charge distribution, which means that it result is like scattering from a point particle, because the wavelength is so large that this is so. Now question is, what happens if Q is large? That means the wavelength is small. Now I go back to my initial formula and I write this whole thing as the following. The differential cross section d sigma d omega is equal to point times f of. So this d sigma d omega point includes the Rutherford times this factor, and I multiply it by f of q square. The question is, how do I measure f of q square? This is d sigma d omega observed divided by where d sigma d omega point is a known function. It is this times this, everything is known. Now what do you expect? This should be a falling factor of q or growing factor of q1. This is how you can measure form factor in principle. Now what do you expect? Let us say q so now it means that I have a small wavelength or large now the small wavelength means now the scatterer is too big, right? The electron is coming, and it means that now it is scattered only from a part of the scatterer. That means it does not feel the full charge of the scatterer, but only a part of the charge of the scatterer. So the electron is scattered from the charge which is large charge therefore so as the magnitude of Q increases, the form factor as measured by this formula, it shows that it drops. So therefore this description agrees with all physical intuition. In the low momentum range, we get back the result for scattering of 2 point-like particles. In the case of high momentum, we get a decrease in the cross section. Therefore, this description makes sense. What we have learned from this exercise is represent the extended object by a function which in this case is at least in because I have this formula. Now I will discuss tomorrow that if I really treat the proton as an extended object, the only good thing that I can do is we represent its departure from point-like behavior by functions. But unfortunately the functions are not calculable as in this case. But exactly as in this case, they can be measured experimentally. Therefore, this gives us a hint that even if the proton is not a point-like particle, if we are smart enough, we can parameterize the departure of the proton from point-like behavior by certain functions. And those functions can help me calculate the result of scattering from protons. Alright, so let us end here today.